right, everybody, welcome back to Natural Language Processing. In this video, we will discuss the topic of n-gram language models, which means we really have two topics to talk about today. Right? Language models, what is a language model and why do we use them? N-grams, what are n-grams and why do we use them? So let's jump into it, right? And let's start by thinking of a sentence, right? If I were to say, the water of Walden Pond is beautifully, well, there's a few words that might complete that sentence, right? A few that would sound natural. For instance, blue or green or clear, right? And there's many, many words that would sound very unnatural, out of place at the end of this sentence. For instance, refrigerator or that. So, language models are a tool that can predict upcoming words, right? So a language model informs us, right, given a string of words, what is most likely to come next, right? And this kind of rests on the concept of a model, right? And when I say model, and this idea of a model or modeling is extremely common in AI and machine learning, right? What I'm talking about is, for instance, a generator, right? Just spitting out words that come next. Think of like GPT or Claude just generating human-sounding text. Or I might be talking about a function, right? A learned mapping between some inputs and some outputs. Or I might be talking about a representation of a thing. For instance, our language. And really, a model is all three at once, right? So word prediction is sort of a measurable and quantifiable task, but by building models who can perform prediction, right? Who can look at some beginning words in a sentence and select the next most likely word in the sentence. Well, I've kind of created a representation of our language, right? We've given ourselves a tool to explore how languages are structured and how they are used. I might also, recognize words that appear out of place, for instance, using there, T-H-E-I-R, when I intended to use there, T-H-E-R-E. Or this could help us with the task of speech recognition, right? If I'm converting the wave form read by a microphone into written text, having some concept of what words belong adjacent to one another can make that task of translating, transducing, right, sound into text more easily, speech into text, right, more easy. So for instance, I will be back soonish is much more likely than I will be bassoon-dish. And some more about why today we're talking about word prediction. Why in this natural language processing class are we talking about word prediction? Well, this is moving us towards a discussion of LLMs, large language models, right? What we're going to do first is understand the concept of a language model, and then we're going to be moving towards what large means in this context and why largeness would be beneficial. But really, large language models are just language models like we've been discussing here, right? Their job is to look at a string of words and pick what's most likely to come next, right? Now, from Intro to AI, I hope that you recognize regression at looking at a sequence and picking a value that is most likely to come next. Well, if we're looking at a sequence itself, right, if we're examining one sentence and picking a word that belongs in that same sentence, well, that's not just regression, that's auto-regression. So that's what we mean when we say that large language models are trained auto-regressively. So let's think about language modeling more formally, right? Let's start to dig out the math behind this idea, right? So let's say we have a sequence of words that we might call W. So here capital W just represents any sequence of words. Well, then I could say that the probability of capital W, that sequence, is equal to the joint probability distribution of each word in the sentence. W sub 1, W sub 2, W sub 3, right? All the way up to W sub n for a sequence of n words, right? So if I want to start performing this task of predicting a word that comes next in a sequence, well, then I need to be able to define conditional probabilities, right? Given an observed sequence, W1 through W4, what do I think the next value is, W5, right? So what is the probability of W5 given that we have seen W1, 2, 3, 4? Okay, so now, how are we going to do this? Right? Well, we're going to do this by counting. Right? And so let's think. I want to know, how likely is it that blue comes after the words, "The water of Walden Pond is so beautifully." All right, so let's count. Right? Let's say, hey, I'm going to count in my corpus every occurrence of "The water of Walden Pond is so beautifully blue." And I'm going to divide that by the count of "The water of Walden Pond is so beautifully." Right? And that will give me the probability that blue follows the sequence, "The water of Walden Pond is so beautifully." And no, that might not work all that well, right? Since "The water of Walden Pond is so beautifully blue" doesn't occur that frequently in any corpus, right? Even if your corpus is just a text copy of Walden Pond, right, you're still not going to see this sentence much, and you're still not going to see the sequence, "The water of Walden Pond is so beautifully" much. Okay, so just the raw count isn't going to work. So here's an idea, right? Let's start thinking about how common each word is individually, right? And then we can apply the chain rule of probability to build up the probability of a sequence, right? Since each one of those words, "The water of Walden Pond is so beautifully blue," is much more likely to occur by itself than that entire sequence is, right? So we'll have a much easier time counting individual words. All right, so let's think about the chain rule, right? And let's think about conditional probabilities. Okay, so if I want to know the likelihood of some joint probability distribution, the probability of A, B, C, and D together, right? Well, that's just the probability of A, the first word in our sentence, times the probability of seeing B given that we've seen A, times the probability of C given that we've seen the sequence AB, times the probability that we see D given that we've seen A, B, C. Right? So the joint probability distribution of any sequence of words, right, x1 through xn, is just that chained sequence of conditional probabilities. The probability of x1 times the probability of x2 given x1 times the probability of x3 given x1, x2, and so on and so on. All right. Well, that's doable all of a sudden, right? Now I can count individual words, and I can build probabilities for much longer sentences out of that, right? So let's think. To get "The water of Walden Pond," to get the probability that those words appear in that order, well, I just need to look at some corpus, some collection of data, right? And the bigger my corpus is, the better I'm going to model the English language in this case. Right? So I need to count, how many times did I see "the"? How many times did I see "water" immediately after the word "d"? How many times did I see "of" immediately after the "water"? And so on and so forth. So let's start thinking simply. Let's start thinking about a simple language model. And in particular, we're going to apply the Markov assumption, right? The Markov assumption tells us that we only have to look one word back to approximate the probability, the conditional probability of a two-word sequence appearing, right? So what we're saying here basically is, if I want to know how likely is blue to follow the water of Walden Pond is so beautifully, right? How likely is it that the next word is blue? Well, that's roughly equal to the likelihood that blue follows beautifully. We only have to look one word back. So this is a simplifying assumption, right? Simplifying means we're abstracting, we're making some sacrifices in accuracy to make our language model easier to compute, right? Because it will be easier to compute. And you've all built a model like this before. In Intro to AI, you all built Markov chain generators or hidden Markov models that could spit out kind of sequences of gibberish, right? But gibberish that sort of looked a lot like sentences of English, right, that we trained on Alice in Wonderland. Okay, right? And this simplifying assumption makes that state machine much, much easier, right? Makes it much easier to code out. And so we're talking about a two-word sequence, right? So let's just come up with a name for a two-word sequence, right? Let's say, maybe bigram, right? Bi for two, and gram is in telegram, right? Which is just a bunch of words. Okay, so the bigram Markov assumption is just this idea that we only have to look at two words at a time to make our counting much more simple. And let's see if this works, right? Let's start looking at some simple language models, right? And then from there, we'll work our way up to some more complicated ones. So let's start with the simplest possible probabilistic language model, a unigram model, right? Bigram means we are looking at two words at once. Unigram will mean, hey, let's just look at one word at a time, right? And let's see how that looks, right? So, here we only have to ask ourselves, hey, how likely is to occur in a sentence? How likely is him? How likely is swallowed? How likely is confess? How likely is here? How likely is both? Right? And we'll notice here that these are all words, right? These are all legitimately words from the English language, but they're not ordered meaningfully, right? We're not obeying any grammar, and we're not conveying any meaning, right? This is just gibberish, right? So a unigram model ignores any ordering, any significance to the order of words, right? And just spits out words that are the most likely to appear. But it did a good job of that. So notice we see to and him and which and of and less and issue, all of which are very common English words, right? And we're not seeing like defenestration or like deoxyribonucleic acid, right? We're not seeing uncommon words appearing frequently. So we've still modeled something. We've still created a simple representation of our language that really only gives us a kind of like a histogram of how frequently words appear. Okay. So let's go back to that Markov model, right? What if we were thinking about bigrams? Now we don't just care about how frequently a word appears. I also want to know how frequently does it follow the preceding word, right? So now we get, why dost stand forth thy canopy, forsooth? He is this palpable hit, the King Henry. Which, if you are the kind of person that, for example, falls asleep to podcasts, right? Or if you like to listen to something while you're falling asleep, these are sentences that if you were like dozing off, if you were sort of incoherently listening to someone speak these sentences, they almost sound like they're structured correctly, right? They almost sound like they're conveying meaning, right? They have kind of the appearance of meaning without any of the actual meaning itself. which means our model is getting a little bit more complex. Our model is becoming a better approximation of the language. Now it's telling us something additional about our language, right? We're modeling some additional aspect of our language, and because of that, we're getting better predictions, right? We have a better refined function between now a preceding word and a succeeding word. All right, and I think we saw good improvement between unigram and bigram, right? We saw good improvement between just looking at one word at a time and then looking at two words at a time. So we might speculate, well, what if instead of una or bi or tri or quad, let's just say n-gram, right? What if we were looking at n different words at a time? Well, and then could my model do a good job of spitting out sentences that sound like reasonable English? Okay, so n-gram language models, right? N words. And there's still a problem there, right? Let's look at this. The soups that I made from that new cookbook I bought yesterday were amazingly delicious. And let's think about the soups and were. Those match, right? The verb were needs to match with that plural noun, the soups. And I'm never going to get that if I'm just looking at strings of sentences after the other, after the other, after the other, right? Maybe if I set up my language model as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, a 13-gram language model, okay, maybe we could capture the relationship between the soups and were. But what we've just seen is the necessity of large language models, right? Large language models don't just look at sequences and say, hey, it'll spit out the next, right? Large language models have a context. Large language models are able to look much, much farther back in a discussion, right, in a transaction than a standard language model. And they're able to capture dependencies between words, right? They're able to sort of pay attention to what words matter in order to predict the next one. So for instance, the soups, a large language model we'll see should be followed by were later in the sentence, not was. All right, but we're still talking about n-gram models, right? And n-gram models are a wonderful way for us to introduce language models and a wonderful way for us to lay some groundwork for tools that will be useful when we get to talking about large language models later in this class, right? So for instance, training and test sets, right? How do we split our data to make it meaningful in training and testing a language model, right? The perplexity metric, right? A new function we can use to measure the performance of a model that we haven't talked about in, say, Intro to AI, right? Sampling to get random sequences out of text, right? Or ideas like interpolation that we'll be talking about later, right? So language models, and particularly n-gram language models, are an important introduction to some very important concepts for later in this class. So stick with me as we talk about n-grams themselves and some more about their significance. Okay, and one seamless edit later, here we are. We're going to get into estimating n-gram probability. So how do we actually start doing this? Right, okay, cool. So if I want to know how likely one word is to follow another in a bigram, right, well that would be, well, let's see, I could just count all occurrences of a particular bigram, so the two words in the correct order, and then sum up a count of every other bigram that appears in the corpus. And you might notice that the denominator in this division is going to be a lot of work to count out. Fortunately, it turns out that this is equivalent to counting the occurrence of the bigram divided by the occurrence of the first word in the sequence, W sub n minus 1. All right, so let's look at an example of this, right? Here we have a very small Seussian corpus, right? I have 3 sentences in my corpus. I am Sam, Sam I am, I do not like green eggs and ham. And we've just filled in some anchors to mark the beginning and end of the string. So that open S and close S kind of HTML looking tags there just mark the beginning and end of a sentence, right? Since, well, if we're going to make a word generator, it's important for us to understand that some words are more likely to occur at the beginning of a sentence, right? Okay, so I want to work out bigrams, right? The probability of each bigram that we see. So I'll need to compute the probability of W sub I given W sub I minus 1. And that means taking account of the sequence W sub I minus 1, Wi, and dividing that by the count of W sub I minus 1. So to get our bigram probabilities, we're going to need to count all of the unigrams, right? Since that's our denominator here. That's how we do our little division. Okay, cool. So what do these look? Well, I see the probability of I following the start of the sentence marker, right? So the top left probability here is essentially just the probability that I starts a sentence. Okay, so we need to look at the sequence start sentence I. I see that in the first and third sentences. Okay, so I count 2, and now I divide that by the occurrences of start sentence, which is 3. So the probability that I starts a sentence is 67%, right? Similarly, the probability that Sam starts a sentence, right? The specific bigram, open S, then Sam occurs once. The particular unigram, open S, occurs 3 times, right? So there's a 33% chance that Sam starts a sentence. Okay, if I've seen I, how likely is am the next word? Well, I is followed by am twice in the first and second sentences, and the count of am is 1, 2, 3. I am Sam, Sam I am. Oh, I'm sorry, I occurs 3 times, not am. I misspoke there. So the likelihood that am follows I is 67%. All right, so that was pretty easy to count, right? And I hope that you were able to work out the rest of these maybe in your head or pause the video and count through them yourself, right? But we should see these bigrams in this tiny corpus are actually pretty easy to get the probabilities of. Okay, so let's use a slightly larger corpus, right? Here 4 sentences, and they're slightly longer, and the vocabulary is slightly more varied. Okay. Well, let's see. Okay, yeah, so using this particular Berkeley restaurant project sentences, I guess they collected people around Berkeley speaking about restaurants. Okay, so they got 9,000 total sentences, right? And we can count the likelihood that I follows I, the likelihood that want follows I, the likelihood that to follows I, or rather, not likelihoods, but just raw counts here, right? So the occurrences of want following I, or I following want, the occurrences of to following want, right? So essentially, this left-hand column would be our precedent, the first word in the sequence, and the row here across the top would be the next word in the sequence, right? So I can get a count of every bigram in a slightly larger data set. Okay. So to get our probabilities, I would need to count how many times does I and want and to and eat, right? We need the unigram counts. And now we can get essentially here, for each raw count for a bigram, we can divide it by the unigram count of the word that comes first in a sentence, right? And for those of you that have taken my data mining class, this might feel or sound a lot like finding frequent item sets, right? Frequent singletons and doubletons and triples, right? Because it's kind of a similar concept, right? Except now we care about word order, whereas item sets, we don't care what order they're in. A set is a set. And now with just my bigram counts, well, I can use that to get the probability of this sentence. I want English food, right? Well, let's see. It's just, how does the sentence start? I starts the sentence. So how likely is it that I starts a sentence? Well, we can look that up in our table, right? And how likely is it that want follows I? The probability of want given I. How likely is it that English follows want? The probability of English given want. Right? And so by multiplying, we see 0.00031. Right? The likelihood of the occurrence of a particular sentence, I want English food, is actually quite low. Right, which depending on your opinions about English food, that may or may not surprise you. But the model has given us some intuition into the structure of our language, right? So, for instance, right, we can calculate that want English occurs, that particular bigram in that particular order occurs, let's say, about 1/10% of the occurrences in this particular corpus, right? Or want Chinese comes up about 6-7 tenths of a % of the bigrams in this particular corpus, right? And it looks like in this particular set of sentences that was collected for this corpus, I starts the sentence about 25% of the time, right? So that really tells us a lot about this corpus, right? What's going on there, right? A quarter of these sentences start with I. A quarter of the occurrences of the word, 2/3 of the occurrences of the word want are followed by to. And we're going to notice something there, right? That if I'm talking about a sequence of words of any substantial length, right? Not just 1, 2, 3, 4, right? But what if it's 8 or 12 or 20 words, right? What if I want to calculate the likelihood of a particular 20-word sentence occurring, right? If I were to calculate an n-gram that long, I'm going to be multiplying together a lot of probabilities. Probabilities are always less than 1, so the more I multiply together, the smaller and smaller that value gets, and eventually we're just going to run out of floating point precision, right? We're going to end up with probabilities that we can't easily represent in a program. So log probabilities are a way to help us avoid those sort of vanishing probability values, right? And that's kind of based on this sort of underlying law of mathematics, right, and how logs work, that the log of a product, right, so the log of P1 times P2 times P3 times P4 is equal to the sum of the logs, right? So now I've got probabilities that I can express as a sum rather than as a multiple, right? And sums, even if these probabilities are smaller than 1, sums always grow, right? So we're no longer going to be sort of running out of floating point precision, right? We'll still be able to represent our probabilities essentially just by storing the number in a different format as a log rather than as a raw probability. All right, so we saw bigrams were pretty easy to compute. 4 or 5 grams or larger n-grams would essentially just be down to doing more counting and more division. So, if you're interested in seeing some 4 or 5 grams, there's been some good research on it. There are some published n-gram collections on the internet that I will leave you to seek out. But for now, we've now seen the concepts of a language model, the concepts of an n-gram. So I'm going to jump over to the coding portion of this video, and we're going to code some of this out together. Okay, so here we are in the coding portion of this video. I've given us a pretty simple challenge for this one. I've got us a paragraph of text that I have borrowed from Wikipedia. It is just a paragraph about the founding of our university. And we are going to find the probability of each unigram, bigram, and trigram in this text, right? So I have already given us our text as a nice, convenient string object here in our Python program. I've already gone ahead and imported NLTK because I know I'm going to need to word tokenize this text. So let's see, tokens, nltk.tokenize.word tokenize. Let's just give it our text, and let's see what we get. Oh, I didn't want to print. I wanted to print tokens. Okay, Saint Ed. Okay, there's some irregularities here. So, for instance, it thinks that Edward and is 2 different words. The right answer for this is to craft a regular expression that will correctly recognize that a word separated by white space can include an apostrophe. I just want us to get to the interesting part of this video, so I'm going to go through and get rid of those apostrophes, right? Okay, cool. So now we want to know the count of each one of these words. And let's see, just for consistency with the slides, I'll go ahead and put in our start string and end string markers too. We're not actually going to be doing any generation in this video. Y'all are welcome to give it a try yourselves. Build yourself an n-gram string generator. This is a very small amount of text to train one of those on. Right, but just for consistency with the videos, I'll go ahead and put in our start string and end string. Okay, cool. So now what we want is to count all of the unigrams. So unigram counts. And I can start this off as a dictionary, right? And now for token and tokens, unigram counts of token is equal to, this is a dictionary, right? So I can use the dictionary method get for this. Get token, comma, if the token isn't in the dictionary already, we'll fill in a 0, and whatever was there, we want to add 1 to it because we just saw it again. And now here, quick as a bunny, are our unigram counts. Here we go. Okay, so open bracket appears once. Alright, so it looks like open bracket, close bracket. That annoys me. I don't want to mess with those. So again, for simplicity's sake, we will make a simplifying assumption and just get rid of those. There we go. Okay, so Saint appears 3, Edwards appears 3, University appears 2, was, surprisingly, only appears 1 time in this block of text. I say surprisingly because 1 is a fairly common word. But okay, we got all of our raw counts. Okay, so let's say we wanted to know the probability of the word Edwards appearing, or university, or founded. Well, that would just be the number of Edwards divided by the total number of tokens. So let's see, total is equal to, I think we can just do sum of unigram counts dot key, not keys, sorry, values, right? Since we want the right-hand side here, the values, not the keys. I'll print our total just to make sure it passes a sniff test. Okay, so 92 total words. That looks like about 92 total words. Okay, so now unigram probabilities, we can say is just equal to, let's see, count, let's see, key, comma, value divided by total for key value in, I don't know, I need to get both the keys and the values at the same time, so I can use the dictionary method items to do that. Items, there we go. I think this will work. We might have to debug a little, but let's just look at our probabilities and see how that worked out. So I will print unigram probabilities, and if I give that a run, I end up with a name error, of course, because total is not defined. Let's use total instead. Okay, so Saint represents about 3% of the words in this. Edwards represents about 3% of the words. University is about 2% of the words. I happen to remember off the top of my head, university appeared twice. There were slightly less than 100 words, so each occurrence is 1% of our total sentence. So yeah, 2% for university makes sense. I think this passes a sniff test, and I think we have got all of our, yeah. Okay, some of them are silly. Comma is showing up as a word. I'm noticing Edward and Edwards are being counted as two different words, right? So refer to the tokenizing video if you want to be able to fix silly issues like this. But plowing ahead, just because we're here to count unigrams and bigrams, right? Not to review tokenizing material. So let's now get the bigram counts. So now let's see, for I, comma, schmoot, and enumerate tokens. So now I want to iterate over all of the indexes in the list tokens. This can be a slightly more elegant way than range len like we're all used to using. Let's see if I can make this work. So I want, let's just print all the bigrams, right? I want 2 words at a time. So it will be, tokens of I to I plus 1. This is going to give me an out of bounds error. So we want to, there we go, cut off the last one. All right, and we don't need to print these probabilities anymore. Okay, let's see, here we go. All of our bigrams, with one small correction, there we go. All of our bigrams, St. Edwards, Edwards University, university was founded, founded by. Cool, okay, good. So now we can do a very similar thing for bigram counts. Start off with an empty dictionary. Here statement. Just borrowing some code. A good coder never writes anything twice, right? Copy and paste as much as you can. I saved this print statement so that I can get that part of it. I need this to be bigram. I need token to be tokens, a list slice here from I to I plus 2. We don't need to print inside the loop. Let's just print bigram counts here. See how we're doing, right? This is just a gut check. So, oh, here we go. That is okay. I can make this a string by joining it using white space. We are getting well into the there might have been a more elegant way to do this territory. But hey, we're committed now. Let's see how it goes. Okay, St. Edward's appears 3 times. Edwards University appears once. University was appears once. Was founded appears once. Congregation of appears twice. Okay, these are believable. These are believable. Okay. So now I want to get all of my bigram probabilities. And let's see. If I refer to our slides, right, we have a pretty simple equation for that, right? It's just the count of the 2 appearing together divided by the count of the first word appearing, right? So this is why we needed all of our bigrams. So let's see. Oh, sorry, this is why we needed all of our unigrams. Probabilities. Let's create ourselves a new all right, so now for W1, let's see, for bigram in bigram counts. I think I can leave it like this, right? What we want to do is iterate over the keys. If I'm remembering correctly, the default behavior of Python, if you iterate over a dictionary, is to iterate over the keys. So let's just check that real quick. Let's make sure I'm not doing something wacky and wild. So yeah, there we go. It's iterating over the keys of our dictionary. So we need to get word 1 and word 2. It's safe to split them on white space because I joined them with a single white space character. All right, so now bigram probabilities. Please autocomplete that for me. Cool. Of bigram is equal to the count of the 2 together divided by the count of the first word by itself, which will be W1. So that is bigram counts of bigram, both words together, divided by unigram counts of the first word by itself, W1. Okay, let's give this a run and print our bigram probabilities. Y'all might be able to hear that word is starting to lose meaning. I need to stop saying bigram probabilities to myself over and over again. There we go. Okay, so it looks like the probability of Edwards given Saint is 100%. Saint is always followed by Edwards. The probability of university given Edwards is 33%. The university of was given university, or sorry, the probability of was given university is 50%. The probability of founded given was, is 100%. So was is always followed by founded. That's kind of cool. All right. Let's see. Let's try sorting this, and then this is always a little tricky to do, but I think I remember how to sort a dictionary. I might actually need to pause the video and Google it real quick, but stick with me. I think I can do this in, let's see, sorted bigram. And bigram probability is dot items key. So how do we want to sort these? Is equal to lambda x equals x of, we want to sort by the values, is x of 1. Ho ho ho, let's see how that went. Nope. Did I forget a comma? Almost certainly. Items, there we go. Okay, 1 second please. And there we go. Y'all probably saw it before I did. I was misspelling lambda. For anyone who didn't know this, this is how you sort a dictionary in Python by its values, which is kind of cool. So let's see. Also, it's in ascending order, which is slightly annoying, but it just means we need to scroll to the end. Okay, cool. So with is always followed by the, affiliated is always followed by with, is affiliated. Right. Y'all will probably notice these bigrams aren't generally true for the language as a whole, but in our little sample of text here, we can see, for instance, Deering is always followed by the. Let's see if we can get back out of the 100%. These are probably 100% because, for instance, here the antecedent, the preceding word institution, probably only occurs once, right? And that's why these counts are so high. Here we go. Okay, cool. So it looks like after we get out of the 100%, we go straight into 50%. Looks like periods are showing up as words. Well, again, tokenizing. Okay, cool. So let's think about counting trigrams. And it shouldn't be too much harder, right? Let's comment this out. I might want to reference that code later. Now let's get our trigram count. Okay. And I'm going to do this the easiest way possible. Just plus 3 plus 3. And I think we've got it. All right, let's print our trigram counts and see how they look. Trigram counts, please, and thank you. Okay, St. Edward's University appears once. Edward's University appears once. Was founded by appears once, right? Notice here, the longer our n-grams get, sort of necessarily, the less frequent they're going to get, the less they show up. So here, at least we do have a couple of them with a count of 2. So the congregation of holy, each appear twice. Okay. But right as our n-grams get longer, they necessarily get less frequent, right? University was founded is always going to show up less than just university by itself, or university was, or was founded. Less than or equal to, I should say. Okay, cool. So now we've got our counts. Let's get our trigram probabilities, and then I think that will be all we need to do in this coding demonstration. Okay, so let's think about this trigram. Let's just think about this trigram. Edwards University was. What is the probability of that showing up, right? So what we want is the probability of was given Edwards University, right? Since that will tell us the likelihood of was following Edwards University. So what is the probability of Edwards University? Well, so that's equal to the probability of Edwards times the probability of University given Edwards, right? So this would be the probability of Edwards times the bigram probability of Edwards University will give us the probability that we are looking for. Yes, so Okay, good. So we know this probability, and as a matter of fact, actually, if we think about what we're really looking for here, right, is we want kind of a joint probability distribution of like what is the likelihood of this showing up, right? And we actually know that that's equal to the probability of Edwards, which we've got from our unigram probabilities, times the probability of University given Edwards, good, times the probability of was given Edwards University. Good, so we know this, right? That's a unigram probability. We know this, right? That is a bigram probability. And to get this, we just need a count here, the same way we did for bigrams. Yeah, except here instead of a unigram count, we'll be using the bigram count of Edwards University. Yes, so we'll need the count of the trigram, which we've got. We'll divide it by the count of the bigram, which we've got. And I think we are off to the races. I think we're good to go. All right, so I'm going to comment all this out so we can reference it without breaking the interpreter. I'm going to steal a little bit of this. I'm going to make this trigram probabilities, right? We're going to give ourselves a new empty dictionary. We're going to iterate over trigram and trigram counts. Okay, we can split all three words. It doesn't really matter. Okay. We want... Okay, and this is where we need to get a little clever. It is equal to, let's see, this. Right? So let's start with just this portion. Good. So it would be the count of word. So it would be the trigram count, of the trigram. I'm going to copy and paste all of this instead of trying to retype it. Retyping it is just inviting typos. and who knows what will happen, divided by the bigram counts of what? The join of W1 and W2. Again, not super efficient, but we are doing this for demonstration, not for workplace efficiency necessarily. Okay, cool. Let's see how we're doing. Okay. Let's just print trigram probabilities. There we go. Make sure, yes, we don't need bigram.split, we need trigram.split. There we go. Okay, so let's see, St. Edward's. So, University follows St. Edward's 33% of the time. Follows Edwards University 100% of the time. Okay, these look believable. These look believable. Except if we want the full joint probability distribution, excuse me. What we really need is all of this, right? The probability of word 1, so that's unigram probabilities of word 1 times the bigram probability of Edwards University and I think we can split this up a little bit just to keep it from getting too messy, times the bigram probability there we go of, let's see, we want this, the first two words smushed together. Yes, that's everything up to there. There we go. Times. All right. And you'll notice this is throwing a little error. I can split up operations over multiple lines in Python by ending them with a single backslash like that. I hope, right? I say that aloud and I know that immediately it's not going to work. But okay, here we go. Cool. So in our text, St. Edward's University represents about 1% of the possible trigrams. Edwards University represents about 1% of the possible trigrams. Right? And that just means, hey, if I took every possible 3-word sequence out of here, right? How many of them would be, for instance, founded by the? Well, we see that is about 1% of our trigrams, right? So here we have a language model, right? That sort of tells us a little bit about this tiny snippet of sentence, and using our conditional probabilities, right? So like just this portion, the likelihood of one word given the preceding bigram. With just those conditional probabilities, we could form a generator, right? We just went like one step farther and went past the conditional probability to get the full joint probability distribution for 3-word sequences, for instance, was founded by, and we see our results here. So I hope that was clear and reasonable. Please feel free to email me or join me in my office hours if you have any questions about anything we've covered in this video. Otherwise, I will see you all back during our class time and, of course, in our next video. Thank you very much for your attention.